Welcome back to Arxflix. Today, we're diving into an exciting paper titled HyperDiffusion, Generating Implicit Neural Fields with Weight-Space Diffusion. This research proposes a groundbreaking approach for generative modeling of implicit neural fields by leveraging weight-space diffusion. Here's a snapshot of the HyperDiffusion model, generating 3D shapes. Let's unpack the core concepts and innovations introduced in this paper. Implicit neural fields use multilayer perceptrons, MLPs, to map input coordinates to signals such as sign distances, providing a compact and high-fidelity representation of 3D and 4D data. MLPs map coordinates, math effects, to target signals with parameters, theta, enabling high-resolution data representation without explicit grids or voxel constraints. Despite their advantages, the lack of a regular grid structure in implicit neural fields makes it challenging to apply generative modeling directly. Traditional methods focus on raw 3D, or 4D surface information, or rely on encoder-decoder networks, which are often computationally heavy. HyperDiffusion revolutionizes this by operating over the MLP weights themselves. By optimizing MLPs to fit data samples and applying diffusion on these weights, it allows generative modeling of high-dimensional data. This figure illustrates the HyperDiffusion framework. It starts with overfitting MLPs to individual dataset instances, then employs a transformer-based architecture to perform diffusion on these MLP weights. The process begins with optimizing MLPs to precisely represent each data sample, flattened into 1D vectors for the diffusion model. By minimizing the binary cross-entropy loss, the MLPs achieve high fidelity in shape representations, crucial for downstream diffusion processes. Once optimized, these MLP weights are used in a diffusion process, modeled by a transformer network. This network predicts denoised MLP weights, enabling the generation of new implicit neural fields. This visual shows the denoising process over time. Noisy MLP parameters evolve into valid shapes, illustrating the power of diffusion in weight space. HyperDiffusion is dimension agnostic. The same methods can be applied to generate high-fidelity 3D shapes and 4D animations, demonstrating its versatility. As shown here, HyperDiffusion successfully generates complex 4D animations as well. HyperDiffusion outperforms state-of-the-art methods in both 3D and 4D shape generation. It achieves better fidelity and diversity compared to previous models, particularly in perceptual metrics. This comparison highlights the superior quality of shapes generated by HyperDiffusion compared to its voxel-based and point cloud counterparts. HyperDiffusion opens new avenues for generative modeling in high-dimensional spaces by focusing on MLP weight space. With its innovative approach, this model significantly advances the field of neural implicit field generation. Stay tuned for more cutting-edge research summaries on Arxflix. Thanks for watching. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.